Hello everyone. In this presentation, I want to introduce the cognitive ratio and spectrum sensing technique. And my focus paper is energy efficient spectrum sensing strategy in cognitive ratio networks. In this paper, a novel metric is proposed to evaluate the average sensing energy efficiency of the cognitive ratio, and a theorem is proposed for determining the optimum number of cognitive terminals in cooperative sensing. Spectrum scarcity has always been the main limit on the growth of wireless services. However, National Racial Network Research Testbed project reviews in 2005 reviews that the average utilization rate of spectrum below 3 gigahertz is merely 5.2%. So this means that current spectrum sources are not used in an efficient way, leading to the spectrum scarcity. Cognitive ratio is proposed as a promising solution to the spectrum underutilization. Cognitive ratio enables secondary users to access licensed bands when the primary users are not present. Thus, spectrum efficiency can be improved without interfering primary users. In cognitive ratio, the first challenge is how to determine whether the primary users are absent or not, which is called spectrum sensing. Spectrum sensing must be reliable to ensure that the second user cause no interference to the primary users. Main spectrum sensing techniques includes energy detection, matched filter detection, cyclostationary feature detection, and eigenvalue detection at all. And each technique has their pros and cons, like cyclostationary feature detection has high computational complexity, often renders it impractical on energy-constrained cognitive devices. And even though energy detection has many drawbacks, such as performance degrades for a low SNR, so reliable detection for a large SNR range maybe not possible. And the energy detection is optimal for independent Gaussian noise samples only. So energy detection has been energy detection has been widely used because of its low complexity. In order to obtain more spectrum opportunities, the cognitive and on the other hand, those spectrum sensing techniques are developed continuously by researchers. The spectrum sensing result gotten only from one cognitive terminal is usually not reliable enough. So cooperative spectrum sensing has been proposed as an efficient approach to improve the sensing reliability by fusing the sensing results from many cognitive terminals and making the final decision in the cognitive base station. That means higher sensing accuracy can be achieved by assigning multiple cognitive terminals to sense one channel. However, the participation of multiple cognitive terminals will cause increase on energy consumption on spectrum sensing and reporting. Thus, firstly, the number of cognitive terminals need to be designed carefully. And then, secondly, because cognitive terminals are typically battery powered, so the energy efficiency is also very important for cognitive ratio networks. And other factors like ISNR and noise variance that can also affect the sensing reliability, but they mainly depend on the behavior of the wireless channel, and designers have very limited control over them. In this paper, a model is made including a centralized cognitive ratio system with one cognitive base station and L cooperative cognitive terminals, and the wideband spectrum is divided into K non-overlapping narrow channels. And cognitive terminals are assigned to detect channels simultaneously, and one cognitive terminal can only detect one channel in one sensing slot. Each cognitive terminal performs local spectrum sensing using the energy detection method, and the OR rules is used for decision fusion in the cognitive base station to make the final decision about the presence or absence of a primary user in each channel. We assume that the primary user signal are subject to rarely fading channel, and they say the probability of false alarm, and they say the average missed detection probability. And in this model, all the local false alarm probability are set to the same value, and for L cognitive terminals and key channels, the missed detection probability can be represented in a matrix. And in this paper, a novel metric is proposed to evaluate the average sensing energy efficiency of the CR network, and it's the eta EE, and this is equation. And the second theorem determines the optimum number of the cognitive terminals is also proposed in this paper. To verify the theorem, Figure 1 shows the average sensing energy efficiency at different numbers of cooperative cognitive terminals. Assume that all cognitive terminals possess same local missed detection probability, and the optimum number of the cognitive terminals can be calculated according to this equation. And this is the calculating result, and this is the simulation result. And we can see that when the proposed metric eta EE is at the highest position, the number of cognitive terminals in the simulation results is well matched with the calculation result. In addition, this paper also extended this metric to the overall average sensing energy efficiency of the entire coordinated spectrum sensing, and cognitive terminal assignment strategy is also proposed in coordinate spectrum sensing for optimizing the overall average sensing energy efficiency. And they compared the performance of the proposed EE iterative greedy algorithm-based strategy and with the iterative Hungarian algorithm-based strategy and the EE iterative Hungarian algorithm-based strategy. The performance of the proposed strategy is close to that of the EE iterative Hungarian algorithm and better than iterative Hungarian algorithm when the number of CD cognitive terminals is over 40. And because of its the proposed its low complexity in calculation, the proposed strategy is its overall performance is better than the EE iterative Hungarian algorithm. And I'm so sorry that I didn't finish this simulation, and I will try my best to do this and show this in the final report. For improvements, in this paper, all the local false alarm probabilities are set to same value, and a predefined threshold lambda is required to decide for the cognitive base station to decide whether the primary users is absent or present. And the common practice of setting this threshold lambda is based on a constant false alarm probability. So this paper, all the false alarm probability are set to the same value. So if they can consider the false alarm probabilities in different situation, and we can get a better threshold, and I think this can improve its simulation results. Okay, that's all. Thanks for listening. Networks has to perform wideband spectrum sensing. However, this is difficult for a single cognitive terminal with constraints on energy and hardware. To address this problem, Chai-Han Lee in 2007 proposed a coordinated spectrum sensing scheme. This scheme divides wideband spectrum into several narrow channels, and then cognitive terminals can be assigned to detect different narrow channels simultaneously.